we are going to look at the nitration of benzene. And be aware this type of a reaction can be done when you have groups on the ring. And depending on what type of a group it is, it can go orthopara or meta. And the way you would know which way it's going to go has to do with, again, the oxidation number of the atom directly attached to the ring. If it's negative or 0, it will be an orthopara director. And if it's positive, it will be a meta director. So when you see this type of a reaction, you would be seeing an aromatic ring. And on the arrow, you would see nitric acid and sulfuric acid. They would be concentrated, so you're just going to add heat. Now, we're going to talk about how you generate the electrophile, because that's really the important part of this. If you want to talk about electrophilic aromatic substitution, I will draw out the steps here, but a detailed explanation of that has been shown previously in a different mechanism. Well, the point of this particular mechanism is to generate the electrophile nitronium ion. And this is done in the presence of 2 strong acids, which is kind of unique. You also have sulfuric acid. Now, typically, 2 strong acids would not interact with each other, but they're actually going to do acid-base chemistry with one another. Now, what it comes down to is who's the stronger acid and who's the weaker acid. So pKa's are the key here. Nitric acid has a pKa of negative 1.4, and sulfuric acid has a pKa of negative 4.8. Under normal circumstances, you would never ever do acid-base chemistry with these guys. But the whole point of this is to do something extreme. You have to do something extreme to make an electrophile. Because normally, aromatic rings will not react. They're aromatic. They're highly stabilized due to their conjugated pi system. And so if you actually want them to react, you have to do something extreme. And this is the something extreme you do. You take these 2 strong acids, and they are concentrated, you mix them together and you heat them up. This is extremely dangerous in terms of the conditions, and I think most of you will get to do this in the lab. But as you can see from these pKa's, sulfuric acid is the stronger acid, so it will act as the proton donor, and nitric acid is therefore going to have to act as the base, which is not what it would normally want to do. So we are going to be donating a proton. Now the question is, which oxygen picks up the proton? You have literally 3 different oxygens. Now, the 2 oxygens on the left, the one with the negative charge and the one with the double bond, they are chemically equivalent oxygens. There's resonance stabilization of that negative charge through both of them. And you could give the proton to the oxygen there with that negative charge. It's a possibility, and it will actually likely go there because charges attract each other like that, a positive and a negative. The problem is, by giving it to that particular oxygen, you have nowhere to go. You have to wait for it to dissociate and literally put it on the oxygen that has the proton. The reason it needs to go to the oxygen that has the proton is we actually have to create a good leaving group, and so this is our only option if you want to create a good leaving group for the next step. So once we've picked up that proton, we've done this acid-base chemistry to make the corresponding conjugate acid-base pair. We have this funky little guy. Now, we have the ability to lose water at this point, and that's the kicker. So the oxygen with the negative charge, it will come in here and form an oxygen-nitrogen double bond. And as that is occurring, nitrogen says, wait a minute, I can't have 5 bonds, so somebody's got to go. And the nitrogen-oxygen bond here is polarized toward the oxygen due to electronegativity. It goes away and pulls that off to produce the nitronium ion, and water. And water is a good leaving group. But this is how you generate this particular electrophile. There's the nitronium ion. Now that you have the nitronium ion, you can do this electrophilic aromatic substitution reaction. So you would have an aromatic ring. I'm going to use benzene, but again, be aware that you could have substituents on the ring. And based on what those substituents are, you need to determine if this reaction is going to add the electrophile, orthopara, or meta. But as you can see, this electrophile has a standing positive charge, so it is attracted to electrons. So it's the electrons of the ring that will donate to the nitrogen. Now nitrogen again cannot have 10 electrons, so you've got to break one of these pi bonds, and it doesn't matter which of them you break. But you will add the nitronium ion to the ring. This is one resonance structure as you add it, and there are 2 others. I didn't draw the one I should have probably directly from the previous slide, but it is a resonance structure. That's the one that would have formed directly from my picture previous. These are the 3 resonance structures you will have showing the resonance delocalization of the positive charge through the ring. This is the carbocation intermediate that forms in electrophilic aromatic substitution. Now, you can, I don't know if it's important that you draw all 3 of them all the time, but you need to be aware that all 3 are there. If you're drawing out a mechanism, you should draw out all 3 to show that there is delocalization of the positive charge through the ring. Now, if you happen to have an electron withdrawing group on the ring, and it were here, here, or here, notice that these positions are the positions that are ortho and para to the incoming electrophile. If it is at one of those locations, this group that you have, you will likely have a 4th resonance structure, because that group would be an electron donating group, and you could make a 4th resonance structure for this carbocation. And that's why, is because these positions are ortho and para to the incoming electrophile. If they were at these other 2 positions, which are meta to that incoming electrophile, notice that the positive charge is never on the carbon in the ring, at those locations. So you would not get the bonus of a fourth resonance structure. I'm going to redraw one of those. You can do it with any one of them. Okay, so at this point in time, something with lone pair electrons in the solution will come and remove the proton on the sp3 hybridized carbon of the ring. And when you're doing nitration, you have HSO4- and water in solution. And water is actually a better choice simply because there's it's got the ability to make a weaker acid if you protonate water compared to the HSO4-. So water will come in here, remove the proton, and this pair of electrons here will come in and make the carbon-carbon double bond because carbon is more electronegative. So when you are done, you've had the ability to add the nitro group to the ring. And notice even now there is resonance delocalization of that negative charge through both of those oxygens. It's just not through the ring. That's why we don't worry about it. You've also got, for our charge balance, a hydronium ion and hydrogen sulfate anion in solution. Those two I don't really care about, but the point is you can do this nitration.